All right, so we're just going to work out a few examples in this video. They're going to be exponential and geometric sequences. Exponential and geometric are the same thing. They're used interchangeably. Number 29 from the textbook, a population grows according to an exponential growth model. The initial population is P0 equals 11, and the common ratio is R equals 1.25. If we recall the formula for recursive population growth, we can say that for exponential models, it's P sub n equal to P sub n minus 1 times R. So for part A, we want to find P1. If I plug in 1 for n, then n minus 1 would equal 0. And we can say that P1 is equal to P0 times R. We know that P0 is 11 and R is 1.25. So P1 would be 11 times 1.25. 11 times 1.25 gives us 13.75. So that's the answer to part A. Part B asks that we find P9. And to do this recursively would be tedious, because to find P9, we'd have to find everything in between. We'd have to say, well, P2 is equal to P1 times R. We know that P1 is 13.75, R is 1.25. And we get 17.1875. And then P3 would equal P2 times R, and so on and so forth. That is the drawback to recursion. You have to do all of the intermediate steps. You cannot just jump to P9, which is why we like to use the explicit formula, which is what part 3 asks us for. So to change the recursive exponential model to the explicit, explicit means we write it as a function. So P as a function of n is equal to, and we're going to start with P0, our initial population, times the common ratio raised to the nth power. So our P as a function of n will be 11 times 1.25 raised to the nth power. And we can jump right to P9, which would be 11 times 1.25 raised to the 9th power. And we get 81.96. So the answer to part B is right here. This is the explicit formula. And the answer to, that is part C. The answer to part B is what's P9. And we got that using the explicit formula. So here's our next example from the textbook. You can pause it here, work them out yourself, see if you get the answer that, and then compare it to mine. Use the steps that we used from the previous slide. You want to practice both recursion and explicit. So find P1 recursively, then come up with the explicit model and use that to find P9. So P1 is going to be equal to 8 times 1.5. P1 is going to equal 12. Now I will write the explicit model. P as a function of n is equal to 8 times 1.5 raised to the nth power. To find P9, we're going to type in to our calculator 8 times 1.5 to the 9th power. And we can say this is the answer to part A. P1 is 12. The answer to part B, P sub 9 is approximately 307.55. And the answer to part C, give the explicit description of the population sequence, and that is P as a function of n equals 8 times 1.5 to the nth power. So now we're on problem 31 from the textbook's exercises, and it says consider the geometric sequence. As we said earlier, geometric and exponential are the same thing. They're used interchangeably. Consider the geometric sequence with a first term of P sub 0 equals 3 and a common ratio of R equal to 2. And part A wants us to find P100. Well, we're not going to do 100 terms recursively. We're going to jump right into the explicit formula. Remember, the explicit model is a function. So we write it as P as a function of n is equal to our initial term 3 times the common ratio 2 raised to the nth power. And to find P100, we're going to evaluate 3 times 2 to the 100th power. 3 times 2 raised to the 100th power. You see that this number is too big for our calculator. The calculator has gone right into scientific notation. So it's 3.8 times 10 to the 30th. And that is our answer for part A. Part B, find P sub n. Well, P sub n is going to equal 3 times 2 to the nth power. So we can define P sub n using the explicit model. And I'm going to modify part C. Instead of adding all of the numbers from P0 to P100, let's do numbers that we don't have to put into scientific notation. So we're going to add P0 through P15. P0 we know is 3, P15 3 times 2 raised to the 15th power, 98,304. Now to find the sum from P0 to P15, our textbook gave us a formula. P0 times R to the nth power minus 1 over R minus 1, where n is the number of terms, and n is 1 greater than the last subscript. So in our case, that means that n is going to be 16, because we're going from 0 through 15. We're going to go 1 greater than the last subscript. And we can now write our formula as 3 times 2 raised to the 16th power minus 1 all over 2 minus 1. 3 times, parentheses, 2 raised to the 16th power, get out of the exponent, minus 1. And because the denominator is 2 minus 1, which is 1, that means our answer is 196,605. Now we can test this out. We can use a program like Microsoft Excel to generate all of the terms for us. So we can use a program like Microsoft Excel to test out the sum of all of the terms. I'm going to call this first column my n and the second column my pn. And my n is going to go from 0 to 15. And I'm just going to center that. So we see that we have n from 0 to n equals 15. I know that P0 for this example was 3. And I know that it's going to equal previous times 2. So Microsoft Excel is going to generate all of these terms recursively. And I see I get my 98,304 from my P15. That's what I had here, 98,304. And now I'm going to go underneath that last term and say equals sum. And I'm going to say add up all of these PN numbers and hit enter. And we got 196,605. And that's what our formula gave us over here. Okay, so let's do one more example with the geometric sum. We'll let P0 equal 100. And let the common ratio be 3/2. Find the sum from P0 through P30. Now our formula says that the sum is P0 times r to the nth minus 1 over r minus 1. So if I'm going from 0 to P30, we said that the n up here in the exponent is the number of terms. And if we're going from P0 to P30, that means we have 31 terms. So we're going to use n equal to 31. So our sum is going to be from P0, which is 100, times our ratio, which is 3/2, raised to the 31st power minus 1, all over 3/2 minus 1. Three halves minus 1 is 1/2. And when you divide by a fraction, it's the same as multiplying by its reciprocal. So we can say we're not going to divide by 1/2, but instead we're going to multiply by 2 over 1. So we can write this as 200 times 3/2 raised to the 31st power minus 1. Let's get our calculator for this. 200 times parentheses. Let's insert our fraction bar, 3 over 2 raised to the 31st power. Let's get out of the exponent, minus 1, close the parentheses, and that's 57525. 57525, 117.77. So once again, we can verify this answer using a tool like Microsoft Excel. Our initial was 100 and our ratio is 3/2. So I'm going to start a new column n and p sub n, starting at 100. Let's call that 0 because we're going from 0 through the 31st term. So 1, 2, 3. Do this by formula, equals 1 plus the previous number. So that's P0 through P30. P0 is equal to 100 equals the previous term times 3 halves could be written as 1.5. And we see that P1 would be 150. And I can drag this. Excel will calculate these terms recursively. And now I can say find the sum. I go to the bottom of the column, equals SUM, parenthesis. I'm going to highlight every number in this column, close the parenthesis, hit enter. And the number it gave me here is 575,25118. Looks like our number. Let's open up the column, see if it gives me any decimals. 575,25117.77. That's a match. So we used Excel to accomplish the same task. That's just a little double check to show that the formula we're using and counting the terms the way that we're doing is getting us the correct response. And Excel is doing it term by term. It's generating all of the terms and adding them up. We're doing this here. We did not generate term P30 at all. We only knew P0 and the common ratio. And then we said from 0 to P30 is 31 terms, plugged all that into our formula, and we got the sum. So there are a few answers that are worked out and with explanation. I hope this helps with the homework.